Topic of this lecture is criteria for a molecule to be infrared active. To have this answer, let us approach with a case study considering carbon dioxide molecule. Now, as I have discussed earlier that infrared spectroscopy is associated with the vibration of a molecule, first we have to analyze the vibrational modes that are present in the molecule CO2. Carbon dioxide is a linear triatomic molecule. The hybridization of the central atom, which is carbon, is sp and it is doubly bonded with oxygen on both sides. Now, since it is linear, the rotation about the bond axis, this is the bond axis, this rotation is restricted. Since the center of mass lies on the axis of rotation, so there will be no moment of inertia and there will be no rotational energy and hence there will be no rotation. Now consider this to be x-axis. Then this will be the y-axis. This rotation is allowed. Consider this laboratory axis to be z. This rotation is also allowed. So number of rotational mode that is active is 2. So rotational modes equal to 2. If the molecule is non-linear, then there will be 3 rotational modes. Let us draw carbon dioxide again. We have to draw it for a large number of times. Now the center of mass will coincide with the carbon atom and it will be able to execute translational motion in 3 directions: x, y and z. So number of translational modes will be 3. Linear or non-linear, whatever may be the shape of the molecule, the number of translational modes will always be 3. And in case of rotational modes, if it is linear, then it will be 2. If it is non-linear, it will be 3. Now, total number of modes of motion that can be associated with a molecule is equals to 3n, where n is the atomicity, that is number of atoms present in the molecule. Then for CO2 it will be 3 into 3, since it is triatomic, so it will be 9. Then the modes left will be due to the vibrational modes. So number of vibrational modes will be (9 minus 3 plus 2). So it is 4. Now one may surprise that how can 4 number of vibrational modes be present in this molecule, because there are only 2 bonds. For one bond we have seen 1 vibrational mode. So for 2 bonds there must be 2 vibrational modes. That is a general expectation, but this is not the case. Vibrational mode involves the composite motion of all the atoms present in the molecule and is not limited within a particular bond. So there will be 4 vibrational modes and I will describe it in detail. Among these 4 vibrational modes that are present in carbon dioxide, one is anti-symmetric or asymmetric. Where there will be compression in one bond and stretching in another bond, and this will alternate. Another mode of vibration is symmetric. Here there will be compression in both the bonds and stretching in both the bonds simultaneously, and the remaining 2 will be bending. I will discuss them one by one. The magnitude of this del plus will be twice that of this del minus, since this del plus will counter these 2 del minus simultaneously. In the first case, carbon dioxide molecule is in the equilibrium position. So the center of the positive and the negative charge will coincide, and the position is at the nucleus of carbon atom. So the distance between the positive and the negative charges is 0. So what will be the dipole moment? As per definition, this is the amount of the charge that is separated multiplied by the distance of separation of the positive and the negative charge center. So in this case, d will be 0, so mu will be 0. So it is devoid of any dipole moment. In the second case of asymmetric stretching, the center of the negative charges comes here, while the center of the positive charge lies within the carbon atom. So it will give rise to dipole moment. The dipole moment will act in this direction, since here it is plus and here it is minus. Again we have 0 going to the equilibrium position. Now in this case, the center of the 2 negative charges will appear here. Here it is del plus, so the dipole moment will act downward here. Again it will be 0. Now if we plot for this dipole moment 0, we get a point here. Now it has a magnitude, so we put a point here. Again it will be 0, so it comes down here. This is in the opposite direction, so we give a point here. Again it is 0, so it will be here. Now it will change smoothly, not that it will jump from 0 to this value. For this reason we will get a smooth oscillation. If I connect this dot smoothly, it gives us a oscillation of the electric dipole. So we get an oscillating dipole moment, electrical dipole moment. This mode periodically alters the dipole moment of the molecule along the direction of propagation of the electromagnetic radiation. Hence, the electromagnetic radiation will interact with the asymmetric vibrational mode of carbon dioxide. So, we can say that the asymmetric mode is infrared active. It is infrared active. Now, the second case, which is the symmetric vibrational mode. Now, in this case, both the bonds gets stretched simultaneously and both the bonds gets compressed simultaneously to the same extent. Now, for this, the center of the negative charges will always lie within the carbon atom. So, the distance of separation between the center of the positive and the negative charges will always be 0, either in equilibrium condition or in the stretched condition or in the compressed condition, whatever may be the case, unlike the asymmetric stretching. So, in all the cases, we will get mu equals to E into 0. So, the dipole moment will remain 0 in all the cases. So, what will happen? It will be infrared inactive. Since there is no dipole moment, there will be no oscillation in dipole moment. So, the oscillating electric field of the electromagnetic radiation will not be able to identify this molecule, since it is devoid of any oscillating electric dipole moment. But here, in case of asymmetric vibrational mode, the oscillating dipole moment that is associated with the vibration, with the asymmetric vibration, that will help the molecule to interact with the electromagnetic radiation. So, it will be IR active and this symmetric vibrational mode will be infrared inactive. The remaining vibrations are the bending vibrations of carbon dioxide. This is the CO2 molecule in equilibrium position. Now, what will happen? Both these atoms will come inwards, and in the next case, they will go in this direction simultaneously. Now, if we consider this to be x-axis and this to be y-axis, then here the bending occurs in the xy plane. Now, this is the z direction. If it now occurs along the z axis, both these two atoms along the z axis, once downwards and once upwards, then it will be in the xz plane. So, there will be two mode of vibration, bending vibrations in CO2 molecule. One is on the plane and another is out of plane. Whatever may be the case of bending vibration on the plane or out of plane, both the cases are exactly similar. So, I will show you only one case. This is the equilibrium position. This is one complete oscillation. Now, what will happen to the dipole moment? Let us check. Similarly, this del plus will bear the magnitude equal to the sum of these two del minus, since overall charge will be 0. There will be no net charge on the molecule. Now see, the center of these two negative charges will coincide with the position of the del plus. So here d will be 0, that is the distance of separation between the two charges. So it will have a 0 dipole moment. In case of this configuration, the center will be here, while the center of the positive charge will be within the carbon atom. This is minus, this is plus. So we have a dipole moment along this direction. Again it will be 0 in the equilibrium position. The center will come here. We will have dipole moment in this direction. Again it will be 0. Now if we plot, what will happen? See, at this point it will be 0 dipole moment. For this we will have a point here. For this it will be again 0. Then we will have a point here. Again we will have a point here. Now the switch is smooth, so we have to connect these dots smoothly. So we see there is an oscillation in the electrical dipole moment. For bending vibrations of carbon dioxide molecule, we get the oscillation in the electric dipole moment, and both these bending vibrations will be thus able to interact with the electromagnetic radiation with its electrical component. Thus, among the 4 modes of carbon dioxide, the antisymmetric or the asymmetric mode is IR active, the symmetric mode is IR inactive, and both the bending vibrations are IR active. Now one thing you must note, that the displacement or the deflections that are shown in the form of vibration are shown in an exaggerated fashion. In reality, the displacement occurs very less and it does not cross 10% of the bond length. Now, as usual, I will give you a homework for this lecture also. The homework is try the entire thing, try the entire procedure that I have applied on carbon dioxide on H2O. So you have to start from the number of modes, and then you have to come to vibrational modes, and you have to mention with these diagrams that which modes are infrared active, which are not. This is your home task. Post it in the comment section.